Have you ever been mid-sentence, you're trying to say one simple word and something completely different comes out?
Oh, all the time.
Like you reach for the salt, but you hear yourself say, pass the pepper. Or, the classic calling your partner by your sibling's name.
That cringy moment, yeah.
It's that immediate feeling where your brain just screams, nope, that's not it.
And what's really fascinating is how fast that happens.
Yeah.
Sometimes you catch it before the sound is even fully left your mouth.
It's like this invisible real-time editing. So today, we're doing a deep dive into that invisible fact checker, the system that monitors, controls, and repairs everything we say.
Welcome to the deep dive. We're going to be looking at the incredibly complex machinery that translates your thoughts into speech, and more specifically, how that system manages the constant threat of, well, failure.
And our guide for this is a fantastic perspective paper.
It is. It's from Nature Reviews Psychology, and it's titled Monitoring, Control, and Repair in Word Production. The author is Nazbanu Nozari, who is affiliated with the Department of Psychological and Brain Sciences at Indiana University.
And her goal seems pretty ambitious.
It really is. Nazari's mission is to pull the study of language production out of its traditional little silo.
And connect it to bigger ideas.
Exactly. To merge it with these broader frameworks of how we learn, how we act, how we make decisions in general. We're going to unpack how the brain is constantly monitoring for conflict and then adjusting on the fly. It's a cognitive battleground, really.
Okay, so to understand that, we probably need to set the stage a little. Because for a long time, researchers in this field were kind of in two separate camps.
Completely separate, almost like they were studying two different brains.
On one side, you had the psycholinguistic approach.
Yeah.
And they were focused on the front end, the cognitive part, so mapping meaning to sound.
How you get from the idea of a cat to the sound Kate.
Exactly. Lexical selection, semantic knowledge, all that abstract stuff. And they talk a lot about the lemma. What exactly is that?
The lemma is, think of it as the abstract word file in your brain. It has the meaning the grammar-like knowing cat is a noun, but it doesn't have the sound information attached yet.
So it's the pure concept.
Just pure concept, yeah. And that's where the second camp comes in, the motor speech approach.
Okay. And they handle the back end.
They handle the back end. They're not that concerned with the meaning. They focus on how you map those sound patterns onto the actual physical motor movements of your tongue, your lips, your jaw.
So less about the what and more about the how.
Exactly. It's much more influenced by motor control research. How we learn to throw a baseball or type on a keyboard. It's about the mechanics of articulation.
So you have this flow. You start with a concept. That's Lex lemma, then it gets its sound and structure, and then finally you say it. Psycholinguistics took the first half, motor speech took the second. It seems so inefficient to study them separately.
And that's the whole point of Nazari's work. The separation made some sense because the jobs seem different. Choosing a word from a million options feels very different from moving your tongue.
But the reality is that mistakes can happen anywhere in that chain.
At any point. And the mechanisms for catching and fixing them might actually be the same.
Which brings us to the first big piece. Monitoring. The brain's quality assurance department.
Right. And the classic theory for how we detect errors was something called the perceptual loop.
Let me guess. It means you perceive your own speech.
Basically, yes. The idea, which was formalized by Levelt in the late 90s, is that you monitor your speech by listening to yourself.
So I hear myself say the wrong word, my brain's comprehension system flags it as an error, and then I fix it.
Simple. Elegant. And it makes a lot of sense, but there's a problem.
There's always a problem.
The evidence just doesn't fully support it. The biggest issue is what we call interspeech errors.
You mean when you catch a mistake before you've even said anything out loud?
Exactly. You're thinking about what to say, you almost think the wrong word, and you correct it internally. There's no sound. There's nothing to hear.
So the perceptual loop can't be the whole story. The monitoring has to be happening earlier and internally.
It has to be. And this is where the paper brings in a key idea from broader cognitive science.
Which is?
Conflict monitoring.
Okay, that sounds like what it is.
It is. It's the brain's fast, implicit, sort of subconscious detection system. And it's not looking for an error, it's looking for conflict.
What's the difference?
Well, an error is an outcome. Conflict is the internal state of competition. So if you're trying to say cat, but the word mat is also highly activated in your brain.
Because they sound similar.
Right. The system detects that high level of competition between the two. That conflict is the alarm bell. It signals a high probability of making a mistake.
So it's not a smoke detector, it's a carbon monoxide detector. It's sensing the invisible danger before anything goes wrong.
That's a great way to put it. When one option is clearly dominant, conflict is low, the system just goes. When two options are fighting for the top spot, conflict is high, and the system might pause or slow down.
And is this a language-specific system?
That's the key. It doesn't seem to be. This function seems to rely on brain regions, like the anterior cingulate cortex, the ACC,
Which is the brain's general all-purpose monitoring hub.
for everything, not just language, which is central to Nazari's argument. Language isn't this special isolated module. It's just another complex action that the brain's general-purpose toolkit has to manage.
So we have this multi-process view then. There's a slow, conscious check. Maybe that's the old perceptual loop.
Right, for when you're carefully choosing your words.
And then there's this super fast subconscious conflict monitoring system doing the heavy lifting moment to moment.
And all of it, as the paper points out, really operates under the big umbrella of reinforcement learning theory. The brain is constantly making predictions, checking outcomes, and tuning the system based on what works.
Okay, so monitoring sounds the alarm, but then the system has to actually do something about it. That brings us to control.
Right. How does the system regulate itself when conflict is high?
And the question is it one big red button for control, or are there different tools for different jobs?
It seems to be different tools for different jobs. Nazari makes a really useful distinction here.
Okay.
So, let's take scenario one, contextual similarity. You're in an experiment, naming pictures. You just named a picture of a lemon, and now you see an orange.
Okay, so they're both fruits, similar concepts. The word lemon is probably still buzzing in my head.
Exactly, there's interference. But your goal is simple. Name what you see now. In that case, the system can usually handle it with local inhibition.
Meaning the orange representation just kind of shoves the lemon representation out of the way?
Precisely. It's lateral suppression, probably happening right there in the temporal gyrus where the words are stored. The stimulus itself provides enough support for the right answer to win.
But then there's scenario two.
Scenario two is trickier. This is where the stimulus itself pushes you in the wrong direction.
Like the Stroop task, where you have to say the color of the ink, not the word that's written.
Perfect example. Or think of a social situation. You have to introduce a coworker you really don't like, and you're socially obligated to say something nice.
So every instinct, every bottom-up signal is screaming one thing, but your top-down goal is demanding something else entirely.
Yes, that's when you need external control. You have to recruit the big guns.
The prefrontal cortex, the PFC.
The brain's executive suite. The PFC steps in to bias the whole process toward your goal, to override that powerful automatic response.
This all leads to something you mentioned earlier, the learning account of control. This sounds really important.
It is. It's a huge shift in thinking. The old view was that you just activate the PFC and your control gets better at everything, like a muscle.
So doing Sudoku puzzles should make me better at, I don't know, not swearing in a meeting.
That was the idea. But the learning account says no, that's not how it works. Control isn't just activating a region. It's about strengthening the specific connections between that general control center, the PFC, and the specific task you're trying to control.
So control is learned for a specific task.
It's learned. And the evidence is fascinating. If you train someone to get really good at control in a visual puzzle, their performance in a language control task often shows zero improvement.
Or it can even get worse.
It can even show reverse adaptation. It suggests you're strengthening the pathways for that specific kind of control, and that doesn't just generalize.
So the controller is general, but the application is highly specific.
Yeah.
That has massive implications for things like stroke rehabilitation.
Absolutely. You can't just train general executive function. You have to practice and retrain the specific control links for language itself. Practice really does make perfect, down to the neural pathway level.
So we've monitored for conflict, we've tried to control the output, but sometimes the error gets through anyway.
It happens.
And that's where repair comes in, the final safety net.
And the properties of repairs are just astonishing when you look at them.
The speed, for one.
The speed is incredible. You can have literally 0 milliseconds between stopping the wrong word and starting the right one.
Which means the right word must have been ready to go the whole time.
It was right there, just a fraction of a second behind in the race.
Yeah.
And repairs are also largely unconscious. We see them in 2-year-olds who have no idea they're even doing it.
And you can even repair one mistake with another mistake.
Yes, which tells you the system isn't necessarily comparing what you said to some perfect known target. It's dealing with the ongoing competition.
So how does this work? What's the mechanism?
This is where Nozari and a colleague, J.L. Burgess, proposed the adaptive repair model. And the idea is borrowed from decision-making theory. It's called respond and check.
Okay, walk us through that.
So at time of the initial moment, the system produces the response that's most active. That's the error. Let's say dog.
Because dog was winning the race at that exact millisecond.
Exactly. But the race isn't over. Processing continues for just a moment longer to time TED plus 1.
A split second later.
And in that extra time, the conflict can resolve. The correct word, cat, which was just behind, finally pulls ahead and becomes the most active thing. So the system does a second check.
And it compares the winner at time t with the winner at time t plus 1.
Right. If the winner at t doesn't match the winner at t plus 1,
Yeah.
the system aborts the first one and immediately launches the second. That's your repair.
Wow. So a repair is just the system producing the winner of a slightly delayed race.
That's the idea. And it's adaptive because it's linked to that conflict monitor we talked about. When the initial conflict is high, the system knows a mistake is likely, so it applies that check process more vigorously. It learns to double-check when it feels uncertain.
It's just incredible to think that every conversation is built on this foundation of constant, high-speed cognitive battles and invisible checks and balances.
It really is. I think we can boil this whole deep dive down to a few key takeaways. Takeaway 1 is that word production isn't a simple linear assembly line. It's a system where everything is happening at once, meaning sound and movement are all co-activated and competing.
Takeaway 2 has to be about that monitoring system.
Absolutely. Our ability to catch mistakes relies heavily on that fast, implicit conflict monitoring. It's the brain's early warning signal, assessing the internal competition before a word is even fully formed.
And takeaway 3, I think it has to be about learning.
Yes, the control and repair aren't just fixed mechanisms. They are profoundly shaped by learning. Our fluency, our ability to control what we say, is a skill built by strengthening specific neural pathways through trial and error.
So when we accept that these core principles from decision-making, things like setting a threshold for how much evidence you need before you act, are at play in every single word we say.
It changes how you think about conversation.
It really does. It means our whole conversational style, how fast we talk, how often we pause, how we correct ourselves, it's all just a reflection of the unique learned settings in our brain.
Which leaves us with a final question for you to think about. If your conversational rhythm is a window into your brain's speed versus accuracy trade-off, what does your personal style say about your internal conflict monitor?
A fascinating thought. Thank you for joining us for this deep dive into the hidden mechanics of your own voice. We'll catch you next time.